Hello and welcome back. In section 1.4 we go over common sets of numbers. So the first property that we'll look at is that of density. So a set is dense if between any two elements from the set there exists another element from the set. So if we have this property where any two numbers you pick from the set have another number from that same set in between them, the set is considered dense. If you can find me two elements of that set that don't have another element of that same set in between them, then you've shown me that the set is not dense. So we'll look at the number sets kind of in the order that we as humans discovered them. And going all the way back when we went from being nomadic, just sort of hunter-gatherers, to farming and settling down and raising crops and raising animals, we had to start counting them. That's where we got the set of natural numbers. One pebble would represent one goat, or one container of grain, whatever it was we were counting. So the set of natural numbers. This one is denoted with a capital N, and that just contains 1, 2, 3, 4, and as high as you need to go. Notice that this set we've encountered under a different name, the counting numbers. We referred to this set as before, but its more formal name would be the natural numbers. As far as what this looks like on a number line, we have the 1, we have the 2, but nothing in between them. We have the 3, nothing in between 2 and 3. We have the 4, but nothing in between 3 and 4, etc. So to show the reader that this pattern keeps happening, Mr. Anderson's notation in this is sort of a clever way of showing it. We use an ellipsis sort of up and to the right, since we're heading to the right. If we're going the other way, we would put them up and to the left of where we're going. So this is saying that no, we still don't have any of the things in between these, but we do have each of these points that are exactly 1 unit apart each. And we can show that the natural numbers are not dense. We just have to pick 2 of them that don't have another natural number in between. So for example, 3 and 4 are in the natural numbers. There are no natural numbers between 3 and 4. So this would be our proof, our evidence that then n is not dense. So basically, every civilization figured out natural numbers. They had different ways of writing them out. They used different bases, things like that. But they all had the concept of the natural numbers. Not every society came up with zero. Some of the ancient societies sort of died out before figuring out that concept. But the ones that figured it out sort of technologically advanced more quickly than the others. If we include the zero, then we have the set of whole numbers. And we've seen this set earlier in the chapter. So 0, 1, 2, 3, 4, and it goes as high as you want it to go. So then as far as what that looks like on the number line, pretty much looks how the naturals looked on the number line as well. Only now we also have the 0. So we have 0, we have 1, but we don't have anything in between them. We have 1 and 2, we don't have anything between 1 and 2, and so on. And again, we show the reader that it keeps going in this direction by putting the ellipse above and to the right of our elements on the number line. So see if you can come up with a reason for me claiming that the whole numbers are not dense. See if you can think of a reason why that would be. Pause it if you need to. Okay, welcome back. So I did state W is not dense, and my evidence for that, I would just pick two elements of the whole numbers. So 0 is in the whole numbers, 1 is in the whole numbers, and there are no whole numbers between 0 and 1. So we've proven that W is not dense. Now, as far as how these two sets are related, if we think back to previous sections, every element of the natural numbers appears here in the list of whole numbers, and the list of natural numbers is not the same as the list for whole numbers. That is what it takes to be a proper subset. So natural numbers are a proper subset of the whole numbers. So next, we'll look at the set of integers. Mr. Anderson uses I. Just as a heads up, most books use Z. The reason most books use Z, the mathematician that came up with the notation for it was German, and Zahlen is the German word for number. He figured out the notation. He got to sort of standardize it. But this book will be using I. But just I did want you to be aware that we have sort of a non-standard notation there. So like before, we have our 0 and we have our 1, but we also have they're opposites. So we have a -1. We have a 2, but we also have a -2. We have a 3. We also have a -3. So this was basically when the society started performing operations on numbers. Subtraction is sort of one of the more basic ones to come right after the idea of adding them up. You start removing things as they're used. So this time we have an ellipse on the right and on the left, since we're heading both towards -infinity and towards positive infinity. As far as our sketch of what this would look like, pretty much like what you saw above. So 0 in the middle, we have our 1, we don't have anything in between. We have our -1 and 0, nothing in between the two of them, and so on. So one ellipsis going up and to the right. One going to the left. And again, above the number line. So see if you can decide if the integers are dense or not dense. Pause it if you need to think about it. Okay, welcome back. So the integers, if I'm going to prove that they're not dense, all I have to do is find two neighbors that don't have another integer in between them. Right here I've got that. So -4 is in, I'll use Mr. Anderson's preferred I. -3 is also in I. And there are no integers between -4 and -3. Sometimes you'll see in math notation this little capital E written backwards. That's sort of math shorthand for there does not exist. So sort of a shorthand that you'll see sometimes. So there does not exist an integer between -4 and -3. So that's our evidence to show that then I is not dense. Now, as far as relationships to the other sets, notice if I cover this much up, this then looks like our set of natural numbers. If I slide over a little bit, there's our whole numbers. So all of the natural numbers are here, all of the whole numbers are here, but neither is equal to the set of integers. So those are both proper subsets. So the naturals are a proper subset of the whole numbers. The whole numbers in turn were a proper subset of the integers. So next we look at the set of rational numbers. This is the first one that I'm not going to be able to write the set in roster notation. So we use Q for this. You'll see why in a moment. So instead of all P over Q, such that P and Q are both in the set of integers, Q is not equal to 0. So why can't I just write you a nice list like I did before with the other number sets? Well, we could start with 0 in the middle, sure. We would probably all agree on that. But then what would be the first P over Q that we would put up there? So one person might say, well, 1/2 is sort of a common fraction. We'll start with that one. Someone else might say, well, our number system is base 10. Why don't we use 1/10? And a third person might say, well, our money goes out to the hundredths. Let's use 1/100th as the next fraction. And there isn't really a right or a wrong next fraction to have. So there's really too many options. There's too many possibilities, and we can't use them all. So there's no way to actually list these things in roster notation. These are dense. No matter how close together you put two fractions, as long as you didn't just give me the same number twice, I can find another one that's in between them. Just a quick example, two numbers that are very close in value. Let's say we have 37 out of 50 and 38 out of 50. Well, if I want to squeeze something in between there, I can multiply top and bottom by 10. So I'm changing the look but not the value. So 370 out of 500 and 380 out of 500. Now I have lots of choices of what to put in between there. So I might pick 371 out of 500. That's in between the two. Or I might have picked 375 out of 500. You can reduce that, of course. But no matter what two fractions you pick, as long as they're not just the same number written two different ways, for example, 1/2 and 4/8, that's just the same number written two different ways. As long as they have different values, I guarantee you I can find another rational number in between them. So Q is dense. No matter how close together we pick two elements, there's another one stuck in between them. One question to think about. Can we write, let's say 4. Is 4 an element of the integers? In other words, can 4 be expressed in this format of P over Q, or P and Q are integers and Q is non-zero? Sure, we can write a division problem of integers that gives us 4. For example, we could just use the classic over 1. You've used that in many of your courses to this point. If you want it to look like a fraction, you're always allowed to divide by 1. And there's nothing special about the 4. We could do that with a 5, a 1, a 2, a 9,000. Any of the natural numbers, we could do it that way. Is 0 in the set of integers? Sure. 0 divided by 1 is still 0. So yeah, that counts. Same thing with our negatives. If this were a -4 instead, sure, -4 over 1, still yes. So all of our natural numbers, whole numbers, and integers are contained inside of the rationals. So the naturals are a proper subset of the whole numbers. Whole numbers are a proper subset of the integers. Well, both of these are proper subsets of the integers. And the integers are a proper subset of the rational numbers. Now, as far as the number line, we can think of it as Mr. Anderson's description is picturing a cloud over the number line. It's not every single point on there. There's an infinite number of rational numbers on the number line, but there's also an infinite number of irrational numbers on the number line as well. So we picture it as just sort of a cloud hanging over the number line. So next we'll look at the set of irrational numbers. We'll use a T for that. So T is the set of all x such that x is a real number. X cannot be written as P over Q. P and Q are integers, Q non-zero. So any real number that I can't write as one integer over another integer. The set of irrational numbers is also dense. So for example, if I have 0.123571128 and it just kept going and going and going, that is one of the sort of hallmarks of an irrational number. Its decimal approximation just keeps going without terminating or without repeating. So terminating decimal 1/2 is 0.5, hard stop at the 5. Or 1/3, 0.33333, and the 3's repeat forever. Irrational numbers won't stop and they won't repeat. Just more and more digits spilling out of them. But if I see another irrational number, all I have to do is go one more place and find something in between. So a value in between 0.123571128.5, for example. So I can always find another irrational number in between any two irrational numbers. Some sort of famous examples of irrational numbers, those of you that are geometry fans, our friend pi. By approximately 3.141592653589979, and it gets a little hazy for me after that. And it just keeps going. So we don't see another 14159 cropping up after this. It's its own sort of unique set of digits. E is another sort of famous number that comes up in calculus. 2.718, and that one also will go on forever. But some other more common ones than the ones that get their own special letters, numbers like the square root of 15. I can find the square root of 9. That's just a nice, neat, pretty 3. I can find the square root of 16. That's a nice, neat, pretty 4. But square root of 15, I can't find a nice, neat, pretty solution to that. This number will go on forever. So it's bigger than square root of 9, smaller than square root of 15, or square root of 16, sorry. So we know it's 3 point something, but that number will go on forever. If you tap it into your calculator, I'm going to go ahead and tap that in real quick. We get approximately 3.8729833 4, and then my calculator rounds it to 6. I don't know if it's a 5 or a 6, but that's as far as mine will go. But this will go on forever. This is just how much my calculator can show me. If I wanted to go out 50,000 places, I could set up a computer to execute that task and find me the first 50,000 places. However far out you want to go, you can go there and still find unique strings of numbers in there. So this is, I believe we talked about this being, we did show the example, I didn't write it down, so this is another dense set. The irrationals are sort of a bigger infinite set than the rationals. Similar to the rationals, as far as on the number line, we would picture this as sort of a cloud over the number line. Now, if we pool together all of the number sets that we looked at so far, then we have what's called the set of real numbers. Set of all x such that x is either in Q or T. So one or the other. R is dense. So you give me any two real numbers, I can find another real number in between them, no matter how tight in you make them. You want them within 1/1,000,000th of a unit apart, well then I'll find a number that's out to the billionths. No matter how tight in you get them, I can find another that I can squeeze in between. So the irrationals are a proper subset of the reals. And then the other string that we found before, the naturals, are a subset of the whole numbers, are a subset of the integers, are a proper subset of the rationals. The rationals are a proper subset of the reals. Now, as far as what this looks like, we can make an Euler diagram out of this since we have proper subsets happening here. So I can visually represent these relationships. So my big box this time, instead of being called U, is going to be called R for the reals. And since throwing these two together make up the whole thing of R instead of two circles, what I'm going to do is just saw it in half and say, okay, here's the irrationals over here, here's the rationals over there. And then within the rationals, remember we have some other proper subsets. So we have the integers. Contained within the integers, we have the whole numbers. And contained within the whole numbers, we have our friends, the natural numbers. So you have kind of a bullseye effect going on the left side of the real number diagram. So that one, it'll take you a couple tries, but we're going to draw this one so many times you'll eventually be able to do it in your sleep. So then we'll place a few elements in our real number diagram. Let's do element root 71. 15, negative 9, 9/16, 0, negative 2/11, square root of 16, and 8/2. Or let's do 10/5. Okay, so we're going to place all these in an Euler diagram of the real numbers. So remember, the real numbers are sort of the big tent that contains all of the stuff that we're looking at. And then within them we have the irrationals and the rationals. Inside of the rationals we have the integers. Inside of the integers we have the whole numbers. Inside of the whole numbers we have the natural numbers. So remember the rules for Venn and Euler diagrams. Every element can go in there only one time. I can't put it in two spots. So square root of 71, let's see, square root of 64 is a nice, neat, pretty 8. Square root of 81 is the next perfect square. So this one is in camp irrational. So it is a real number. It is also an irrational number. So that belongs to two sets. The 15, that would have gone in our very first set of numbers we learned about, as well as the whole numbers, the integers. 15 over 1 is 15, and it's rational, so it's also real. That goes all the way into the middle of our bullseye there. I'm just going to kind of check these off as we do them. Negative 9, it is not a natural number. It's not a whole number, but it is an integer. It is a rational number, and it is a real. So it belongs to those three sets, as opposed to the 15 that belong to 1, 2, 3, 4, and 5. 5 of the number sets given. 9 over 16, I can't do anything to sort of simplify that. So we know we're for sure outside of the integers, since the integers were just the whole numbers and their opposites. But 9 is an integer, 16 is an integer, so that makes it a rational number, a P over Q format. So 9 over 16 goes out here on the left side. 0, not a natural number. That wasn't in our counting numbers, but one number set out from there, the whole numbers, it was. So 0 is a whole number, an integer, a rational number, and a real number. Negative 2/11, similar to the 9/16. Negative 2 is in the set of integers, 11 is in the set